Okay, good day. So for this lesson, we will be tackling about redox reactions or oxidation and reduction reactions. So in redox reactions, we look into chemical changes that occur when the electrons from one reactant to another are transferred and forming respective products. So from the term redox, it's actually from two terms. First is oxidation, that's the loss of electron and an increase in the oxidation number of the element in the reactants. The opposite is reduction, which is the gain of the lost electrons from the oxidation reaction, and we call this one again as a reduction reaction. So the electrons will be gained and the resulting compound or element that gained the electrons will have a decrease in the oxidation number. So essentially, for any reactant A that undergoes oxidation, that reactant becomes oxidized, and we will call that one as a reducing agent. So in the oxidation, there is a loss of electron. You can remember this by using the term Leora, which means losing of electrons, oxidation, reducing agent. And then for another reactant, that will be the counterpart for the oxidation reaction, would be the reduction reaction. So the element or compound coming from the reactants will gain the electrons. So if there is an element or reactant that will lose the electrons, there will be also a reactant or an element that will gain those lost electrons. So upon gaining those electrons, that particular element or reactant becomes reduced, and we call it as the oxidizing agent. So for this one, you can remember this by the term or the acronym GEROA. So GEROA means gain of electrons, reduction, and oxidizing agent. So again, LEORA, Leora, that's loss of electrons, oxidation, and that would be a reducing agent. For GEROA, GEROA, that's gain of electrons, reduction, and that is called an oxidizing agent. So, for us to identify redox reactions, we first need to know the rules for assigning oxidation numbers of the elements in the reactants as well as in the products. So, one rule is that oxidation of any monoatomic ion is equal to its ionic charge. So, for example, if you have calcium 2 plus as the ion as part of the reactant, then its oxidation number is also plus 2. Now, for hydrogen, in almost all of its compounds, it will tend to have a positive 1 oxidation number. And then for oxygen, it tends to have negative 2. Now, if you have an elemental free state, or what we call also as an uncombined element, it will always have a 0 oxidation number. For neutral compound, so if we're talking about reactants or products that are neutral, meaning there is no net charge, or the net charge of the product or the reactant is 0, then the sum of the individual oxidation numbers of the atoms should also equate to 0. Then for a polyatomic ion, the sum of the oxidation numbers should also equal to the ionic charge of the ion. So for example, if you have the carbonate ion, which is CO3 2-, then the overall oxidation number combined with the respective elements carbon and oxygen should equate to negative 2. Okay, so for example, we have here CO2 or carbon dioxide. So when we try to find the oxidation numbers for each, we just need to remember a few of those rules. So we know the rule for oxygen, that's negative 2. Then we can compute for carbon. So In the case of this one, we can start with an equation as shown here. So we have oxidation number of carbon plus 2 times the oxidation number of oxygen is equal to 0. Again, from the rules, we know that oxygen is negative 2. So we can substitute that there and equate it again to 0. So 2 times negative 2 is negative 4. And we can further reduce this equation as oxidation number of carbon minus 4 is equal to 0. Equate or transfer negative 4 into the right hand side of the equation, and that becomes a positive 4. Therefore, carbon is positive 4. Now, another example would be for this polyatomic ion, which we know is the sulfate ion. So you have SO4 2 minus. That means the overall net charge would be negative 2. So for this case, we know in the rules that oxygen will be negative 2, so we can solve for sulfur. Then we can write this one as an equation. So we have oxidation number of sulfur plus 4 times the oxidation number of oxygen, since there are 4 oxygen atoms, is equal to negative 2. We know that oxygen is negative 2, so we can substitute the negative value for oxygen. Then we will get oxidation number of sulfur plus negative 8 is negative 2. Again, simplify, we get oxidation number of sulfur minus 8 is equal to negative 2. Transfer negative 8 or minus 8 into the right hand side of the equation, that will become plus 8. So oxidation number of sulfur is equal to negative 2 plus 8, which is positive 6. So sulfur here is positive 6. So for your learning task, find the oxidation number of the central atom for each of the compounds shown. You can write this one in a 1/4 sheet of paper, which will be collected during the final exam. Now, we expand this idea into the atoms of chemical reactions. So say, for example, we have here a reaction between sodium hydroxide and hydrochloric acid to form sodium chloride and water. So we can identify the oxidation numbers of each of those elements present between reactants and products. So we know that oxygen is always negative 2 from the rules, and hydrogen is plus 1. Since sodium hydroxide is a neutral compound, we can say that sodium here is positive 1, which you can also remember in terms of what group sodium is. So that's group 1A. So all group 1A, when they become ions, tend to be positive 1. Then for hydrochloric acid, we know that hydrogen is plus 1. So this is neutral, therefore chlorine or the chloride ion should be negative 1. Then we have sodium chloride. So we know that chloride is negative 1. We also know that sodium is positive 1. And then for water, we know that hydrogen is plus 1. There are 2 hydrogens there, so all in all that's plus 2. And we know that oxygen is negative 2, and that will equate to 0. So this is how you apply the identification of oxidation states of the atoms in a chemical reaction. Now, let's say we have this actual redox reaction. This is magnesium and hydrochloric acid to form magnesium chloride and hydrogen gas. So this is mainly a single displacement reaction, which is a hydrogen displacement reaction, and this tends to be a redox reaction. Why? So we can check each of the elements. So for magnesium, that would be 0. Again, recall the rules that if the element is in its free state, meaning it's still uncombined from other elements in the chemical reaction as represented, then its oxidation number would be 0. And then for hydrogen, for hydrochloric acid, we know that it's always positive 1, therefore the chloride is negative 1. And then for magnesium chloride, we know that chlorides would be negative 1. There are 2 chlorides in the formula, so it will be negative 2. Therefore, magnesium is plus 2. Or you can refer to some of the rules, additional rules, that group 2A or the alkaline earth metals, when they become ions, tend to be positive 2. Lastly, for hydrogen, we know this is still uncombined with other elements, so this is in its elemental free state, so this would be 0. Now, as you can see from the um, identification of the oxidation numbers, you can see that magnesium from reactant to product is from 0 to plus 2. Therefore, it loses 2 electrons. So that's from 0 to positive 2, meaning 2 electrons are lost. Since electrons are lost, remember Leora, so the process is oxidation. And that means magnesium is our reducing agent. And then, we can also inspect for hydrogen, which is from plus 1 to 0. This means that it gained 1 electron for each hydrogen, but in the equation you have 2 hydrogens involved, so all in all it also gained 2 electrons. Okay, so since it gained the 2 electrons, the process is reduction, or it has been reduced, and the hydrochloric acid as a whole would be the oxidizing agent. So again, gain of electrons, reduction, oxidizing agent, so that's Jeroa. Okay, for another example, we have here permanganate ion, MnO4 negative, and sulfurous acid, H2SO3, that would yield to manganese 2 plus and bisulfate ion. So, again, we can identify the oxidation numbers of each of the elements. We can start off with oxygen in permanganate ion, which you know is negative 2. There are 4 oxygens in permanganate ion, so that would equate to negative 8. Negative 2 times 4 is negative 8. Since the overall charge of the ion is negative 1, therefore manganese here is plus 7. And then for the sulfurous acid, or the hydrogen sulfide, we know that hydrogen is plus 1. There are 2 hydrogens, therefore that's plus 2. We also know that oxygen is negative 2. There are 3 oxygens, that's negative 6. So to equate this one to 0, sulfur therefore should be positive 4. So that positive 4 for sulfur, positive 2 for all the hydrogens, and negative 6 for all oxygens will give you a neutral compound. And then we have on the product side manganese 2 plus. This is a monoatomic ion with its charge shown, therefore its oxidation number is also positive 2. And then for the bisulfate ion, we can start with hydrogen, that's always plus 1, and the oxygen is negative 2. So there are 4 oxygens, so that would be negative 8. For this ion, since the overall net charge is negative 1, therefore the sulfur here should be plus 6. So that plus 6 for sulfur, plus 1 for hydrogen, that would be plus 7, and negative 8 from the oxygens will have a residual charge of negative 1. Now, we can inspect the identified oxidation numbers, and we can see that manganese is from positive 7 to positive 2. Therefore, this one gained 5 electrons, and the process is reduction. Therefore, permanganate is our oxidizing agent. For sulfur, that's plus 4 to plus 6. Therefore, it loses 2 electrons and undergoes oxidation, and we call the dihydrogen sulfate as reducing agent. So now, how do we balance this reaction since this is still unbalanced? So let's proceed with balancing by redox. So there are 2 ways depending on the given conditions. So if we consider the entire equation as an acidic medium, then we can first separate the equation into 2 half reactions. We know that the oxidation would be between the dihydrogen sulfide and into bisulfate ion, and the reduction would be permanganate into manganese 2 plus. In continuation, we can balance the atoms other than oxygen and hydrogen in each half reaction. So in this case, you can see that each sulfur is already balanced and each manganese is also already balanced. So we can proceed with the next step, which is to add H2O to balance oxygen atoms and hydrogen atoms to balance, or H plus to balance the hydrogen atoms. So if we inspect the oxidation half reaction, we can see here that there's a discrepancy of oxygen between the hydrogen sulfide and bisulfate ion. So in the reactant side, we are deficient with one oxygen. Since there are 3 oxygens on the reactant side, there are 4 oxygens on the product side. So we can balance this by adding H2O to the reactant side. Now, since we have balanced the oxygen, then we need to balance the hydrogen. So all in all, in the reactant side for the oxidation half reaction, there are 4 hydrogens, and there is only one hydrogen in the product side. So to balance this, we add equivalent 3H plus ions. For the manganate or permanganate and manganese, we can add 4 H2O molecules in the product side, and equivalently we have 8H plus. Since there are 8 hydrogen atoms in the product side, so there should also be 8 hydrogen ions on the reactant side. And then add electrons to each half reaction to balance the charges. So although we have already balanced the number of atoms in each of the reactants and products for each of the half reactions, we also need to balance the charge. So for the oxidation half reaction, overall charge in the reactant side is 0, since H2O and H2SO3 are neutral. Then for HSO4 negative, that's -1, and 3H plus, that's +3. So all in all, there's a net of +2. So since the reactant side is 0 or neutral, then we need to add 2 electrons on the product side. We can account for these 2 electrons, since if you recall, the sulfur in H2SO3 is +4, and the sulfur in HSO4 negative is +6. So there's the difference of 2 electrons. So those are the 2 electrons being lost in the oxidation process. For the reduction, we have here 8H plus and -1 for permanganate. So the overall charge here is +7. Whereas on the product side, Mn2 plus would give us +2 only. So to balance the charge, we can add 5 electrons on the reactant side. Again, we can account for these 5 electrons based on the idea or the fact that previously we identified that manganese is +7 in permanganate ion, and manganese 2 plus is of course +2. So the difference between +7 and +2 is 5 electrons, which is shown here in the reduction half reaction. Now, if necessary, equalize the number of electrons in the 2 half reactions by multiplying the half reactions by appropriate coefficients. So in this case, we have 2 electrons on the oxidation and 5 electrons on the reduction. So to balance this, we need to multiply the entire oxidation half reaction by 5 and the entire reduction half reaction by 2. So the result would be these 2 half reactions. Now we can then combine the 2 half reactions together and balance the final equation by inspection. The number of electrons on both sides must cancel. So as we can see here, we have 10 electrons which are cancelable, and then we have the 15H plus cancelable to the 16H plus, which will have a remainder of H plus on the reactant side. And then for H2O, there are 5 versus 8, so the residual H2O in the product side would be 3. Then we can combine the entire equation into this form. Afterwards, we can then verify the number of atoms and the charges as being balanced. So if we inspect the manganese, we have 2 for the reactant side and 2 for the product side. We can also see that there are 5 sulfur atoms in the reactant side. There are also 5 sulfur atoms in the product side. And then for oxygen, For permanganate, you have 4, but there's a coefficient of 2, so 2 times 4 is 8. For the hydrogen sulfide, we have 5 times 3, 15, so 15 plus 8, that's 23. On the product side, we have 5 times 4 for the oxygen from the bisulfate ion, so that's 20, and 3 oxygens from the 3 H2O molecules, so that's also 23. Lastly, for hydrogen, we have 1 H plus and 5 times 2, 10 from the bisulfate, dihydrogen sulfite, so that's 11 hydrogens in the reactant side. And then for the product side, we have 5 for the hydrogen sulfate and 6 from H2O. All in all, that's also 11. So we have balanced the number of atoms. And then for the charge, we have H plus is positive 1, of course, and permanganate is negative 2. So residual charge for the entire reactant side would be negative 1. For the product side, we have 5 moles of hydrogen sulfate, which is negative 1, so that's negative 5, and 2 moles of manganese 2 plus, which is positive 4. So negative 5 and positive 4 will also give a residual charge of negative 1. So that means the entire equation now is balanced. And that's for acidic medium. So for reactions in basic medium, so if we consider it to be a basic medium, just add both sides equivalent OH minus for the equation for every H plus that appears in the final equation. Okay, so by basic medium, if we're going through the entire reaction process, so remember we have the oxidation half reaction and the reduction half reaction, and then from this we can balance the oxygen and hydrogen atoms and also add electrons later on. So for this case, we still add the same amount of H2O and 3H plus. And then for the reduction, we have 8H plus and the corresponding 4 H2O molecules. Now, the additional step is to add OH to both sides of the equation for every H plus that appears. So for the oxidation half reaction, we add 3 OH minus on both sides. This will then yield to 3 OH minus on the reactant side, and then the 3H plus and the 3 OH minus in the product side will give you, of course, H2O. So we can cancel the H2O on the reactant side with one of the H2Os on the product side. So the result would be this final form of the oxidation half reaction. For the reduction half reaction, we can also add the same amount of OH minus with respect to the amount of H plus present. So we add this or those OH minus in both sides, which will also give us 8H2O and 8 OH minus on the product side. We can then cancel the H2Os within the reactants and products to simplify the equation as shown. So we have 4 moles of H2O and 1 mole of permanganate ion to form manganese 2 plus and 8 OH minus or 8 moles of hydroxide ion. From there, we can then balance the number of electrons, or we can add electrons first to the oxidation half reaction and to the reduction half reaction, and then we multiply the half reactions with their appropriate multiplier. So in this case, we still multiply by 5 and multiply by 2, resulting to these half reactions. And then from there, we can cancel the number of electrons as well as the OH minus and the number of water molecules. So we have 10 electrons, which we can cancel out, and then we have 15 OH minus versus 16 OH minus, so we will be left with 1 OH minus on the product side. And then for H2O, we have also 2 as the residual. So upon combining, we should get these equation. Okay, so again, for checking, we have two manganese atoms, each on the reactant and the product. We have also 5 sulfur atoms for both reactants and products. Then we have um, 23 oxygens in the reactant side. That's 5 times 3 and 2 times 4. So that's 15 and 8, so 23. For the product side, we have 5 times 4, and then 2 times 1, and of course 1 oxygen from the hydroxide ion. So we have 23. And then for hydrogen, you have 2 times 2, 4 for the oxygen, and for the hydrogen in water. And then we have hydrogen in OH minus. So we have also 5 from the HSO4 minus. So that's 10 hydrogen atoms. Now for the hydrogen atoms in the reactant, we have 5 times 2. That's 10 also. So that means in terms of the number of the atoms, that's already balanced. Now we can check for the charge. In the reactant side, you have 2 moles of permanganate ion, so that's negative 1 times 2, that's negative 2. For the product side, we have 5 times negative 1 for the hydrogen sulfate, so we have negative 5. Then again, we have 2 times positive 2 for manganese, that's positive 4. So that's negative 1 in terms of the difference between the two. And then we add one more negative value from the OH minus, so that's also negative 2 in total. So both reactants and products also have a net charge of negative 2, which means the equation is balanced. And that is in terms of a basic medium. So an OH minus is seen from the balanced equation. Again, for the acidic medium, usually you have also a residual H plus, whereas for a basic medium, you have a residual OH minus. Okay, so for your assignment, you have these two reactions. The first one will be balanced via acidic medium, and then the second one will be balanced via the basic medium. All answers will be collected during the final exam.